the last lecture we have discussed the properties of Fourier transform. In this lecture we shall consider another important aspect of Fourier series, that a Fourier transform, which is known as Fourier integrals. Let me recall that if we have a function f of x, then it can be written as 1 upon root 2 pi summation or integration over this dk, where ak is written as dx. Now if we replace this definition over here, if we replace ak by this, then we must write it as 1 upon 2 pi integration. All the integrations are from minus infinity to plus infinity. So we write dk e to the power I k x, then for ak we write this one. So here we use the x prime. So the result is 1 upon 2 pi integration over dk to the power I k x minus x prime. This expression, look at the left hand side. Left hand side, it is function of x, which is expressed in terms of function itself. This is known as Fourier integral. This is known as Fourier integral. If we want to see whether this works or not, you integrate this part with respect to k, that will give you a delta function in x minus x prime, and when you integrate this, we will get back this. So the result is correct. So this is known as Fourier integral, which expresses the function in terms of itself. There are other forms of Fourier integrals which are found in literature, which splits the function in sine and cosine terms. So this is one Fourier integral, important Fourier integral form of Fourier integral. There are other integrals which we shall discuss now. The latter definition starts from the trigonometric Fourier series. So this is f of x Now let us start with trigonometric Fourier series. we apply this to a function f of x, which is defined between a symmetric limit plus minus L. So the function itself is a0 by 2 plus summation over n is equal to 1 to infinity an cos of n by x by L plus bn sine of n by x by L. We know the definition of a0. One upon 2L integration from minus L to plus L fx dx an minus L to plus L dx, and for Vn it is for Vn dx. We first consider what happens to the relation, what happens when L tends to infinity. When L tends to infinity, let me first come to the term a0. Then a0 becomes limit L tends to infinity 1 upon L f of x dx from minus L to plus L. Now we have assumed that whenever we are expanding a function in Fourier series, then this integration is finite and exists. So this integration exists, and when we multiply by divide by L, this must go to 0. So the simplification of Fourier series that we obtained when we extend the range to infinity, that this term reduces to 0. So under such condition, this is the Fourier series. It consists of all the term an and bn starting from n is equal to 1 to infinity. We rewrite this as then we multiply by delta n, where delta n is equal to 1, so we can multiply it by delta n. We introduce a quantity k is equal to n pi by L, so that delta n is equal to L upon pi delta k. So the result becomes this, we write cos of kx, and this we write bn sine of kx multiplied by L by pi delta k. When L tends to infinity, when L tends to infinity, delta k tends to 0. You see that delta k is equal to pi delta n by L, and this tends to 0 as L tends to infinity, because this is equal to 1. So when we consider that in the L tends to infinity, in that limit L tends to infinity, this becomes a integral. This summation is replaced by an integral, and we write it as ak cos kx plus bk sin kx dk, where we define ak as limit L tends to infinity, L by pi times an. This is equal to limit L tends to infinity, L by pi, and from the definition of an 1 by L comes, and then minus L to plus L, f of x cos of kx dx. On simplification, this becomes 1 by pi integration from minus infinity to plus infinity f of x cos of kx dx. When we integrate this out, the resulting quantity is a function of a of k, so this is the definition. Sorry, it should be minus infinity. And similar we have replaced this sum by integral, so this should be from 0 to infinity, so it was correct. And the bk similarly is defined as 1 upon pi limit minus infinity to plus infinity f of x sin kx dx. This is also known as Fourier integral. This is another form of Fourier integral. So there are two alternative forms of Fourier integrals. One is in terms of this complex Fourier series, and another one is from trigonometric Fourier series. So we write another transform as this result. Alternatively, definition is f of x with a of k 1 upon pi and This is a Fourier transform pair. Special situation let us consider a function fx to be even. If fx is even, f of x is even, then we see that this is an even integral. So a of k becomes two by pi 0 to infinity f of x cos kx dx, and since it is even and the sign is an odd, so product is an odd and bk is 0. So we can write of an even function only in terms of this. You need not to write this. And when f of x is equal to this is the simplified version of Fourier integrals, and if f of x is odd, then you see f of x is odd, then a of k is defined, it is odd even, so the result is odd, and we will have ak is equal to 0 and bk will be, coming to the bk term, it is odd, so product of two odd function is an even function, is equal to 2 upon pi f of x sine of kx dx from 0 to infinity, and the function is 0 to infinity bx sine kx dx. This pair of integral is called Fourier cosine integrals. Fourier cosine integrals. This is different from Fourier cosine transform, and this is known as Fourier sine integral. By this we finish our, or we have covered up the theory related to Fourier transform. In the next class onwards we shall discuss the examples of Fourier series. Let me first in today we shall consider, in this lecture we shall consider two simple examples of Fourier transforms. We first consider a delta function and its Fourier transform, what will be its Fourier transform, and see what happens to the case pictorially. One is example 1, f of x is equal to delta x minus x0. So what will be its Fourier transform? For fx we write this. and using the property of delta function, this is x0. So what will be the pictorial representation if we have a k where x basis? So this is x, this is fx. Fx is x minus x0. So at x is equal to x0, the graph will have a sharp peak. This is, and what is the Fourier transform of it as, this is k and this is ak. We see that it is a sinusoidal wave. Sorry. So this is the Fourier transform of delta function. Now we come to the another example, that is the function is a constant function. In x basis, the function is a constant. So example 2 is f of x is equal to c. So a of k we see that it will be a delta k, delta minus k, and it will be a delta function provided we have 2 pi. So the result is root 2 pi c and then delta of k. Since delta function is an even function, it is immaterial whether it is plus k or minus k. So we have, if we have a function f of x is equal to constant c, then its corresponding delta function will be, corresponding Fourier transform a of k will be a delta function. From next class onwards, we shall consider more involved problems which can be solved without the use of contour integration. Will be discussed in the next class onwards.